Stars are not eternal. They may appear constant in our night sky, but they experience a life cycle just like us. From their birth in stellar nurseries to their eventual demise, stars undergo a fascinating journey. They are born, they mature, and ultimately, they die. This life cycle can span millions to billions of years, depending on the star's mass and composition. And some stars certainly know how to make an exit. Their final moments can be some of the most dramatic events in the cosmos. When massive stars exhaust their nuclear fuel, they can no longer hold themselves against the relentless inward pull of gravity. This marks the beginning of their spectacular end. This leads to a catastrophic collapse, a cosmic implosion that triggers one of the most powerful events in the universe, a supernova. The core collapses, and the outer layers are violently ejected into space. Supernovas are not merely explosions. They are the spectacular death throes of stars many times more massive than our own sun. These explosions are so powerful that they can outshine entire galaxies for a brief period. Imagine a star, much larger than our sun, suddenly brightening to outshine an entire galaxy. This incredible burst of light and energy is a supernova. That is the sheer power of a supernova. These events are not just visually stunning, they play a crucial role in the universe. These celestial explosions release an almost unimaginable amount of energy, briefly outshining all the stars in their galaxy. The energy released can be equivalent to the output of an entire galaxy over several years. The light from a single supernova can be so intense that it can be seen across billions of light years. This makes them valuable tools for astronomers studying the distant universe. But some stars take their final bow to an even grander scale. These are the hypernovas, which are even more powerful than supernovas. Hypernovas, as their name suggests, are supernovas on steroids. They are the result of the death of exceptionally massive stars, often more than 100 times the mass of our sun. They are among the most energetic events ever observed. The sheer scale of these explosions is almost beyond comprehension. These colossal explosions occur when exceptionally massive stars, exceeding 100 times the mass of the sun, meet their demise. The resulting explosion is far more powerful than a typical supernova. The energy released during a hypernova is hundreds of times greater than a typical supernova. This immense energy can have far-reaching effects on the surrounding space. They are thought to be the source of the most powerful gamma-ray bursts, brief but incredibly intense flashes of gamma rays that signal the birth of black holes. These gamma-ray bursts can be detected across vast distances. These events are so powerful that they can be detected from across the observable universe. The study of supernovas and hypernovas not only helps us understand the life cycle of stars, but also the evolution of galaxies and the universe itself. The universe is a vast and diverse place with stars of all sizes, colors, and lifespans, so it should come as no surprise that not all star explosions are created equal. We've discussed supernovas and hypernovas, but several other types of stellar explosions light up the cosmos. Each type of explosion has unique characteristics that provide valuable insights into the lives and deaths of stars. Novae, for example, are much less energetic than supernovas but still impressive. They occur in binary star systems where a white dwarf, the dense remnant of a sun-like star, pulls material from its companion star. This stolen material builds up on the white dwarf's surface, eventually triggering a thermonuclear explosion. Unlike supernovas, which destroy the progenitor star, novae can recur as the white dwarf continues to accrete matter. Another type of stellar explosion is the luminous red nova. This relatively rare event occurs when two stars collide or merge, resulting in a burst of light that can last for weeks or even months. The exact mechanisms behind luminous red novae are still being investigated, but they offer a unique opportunity to study stellar interactions and evolution. These various stellar explosions paint a vibrant picture of the dynamic nature of our universe. By studying them, we gain a deeper understanding of the life cycles of stars and the processes that shape galaxies over cosmic timescales. The sheer power of star explosions has captivated astronomers for centuries. These cosmic events, known as supernovae, are among the most energetic and spectacular phenomena in the universe. They can outshine entire galaxies for a brief period, leaving behind remnants that continue to intrigue scientists. But how do these celestial events actually occur? What triggers such a massive release of energy that can be seen across vast distances in space? The answer lies in the heart of stars, where nuclear fusion reigns supreme. This process involves the fusion of hydrogen atoms into helium, releasing enormous amounts of energy that powers the star and produces light and heat. Throughout their lives, stars are engaged in a delicate balancing act. This balance is between the inward pull of gravity and the outward pressure generated by nuclear fusion in the core. Gravity constantly tries to pull the star's material inward, while the outward pressure generated by nuclear fusion in the core pushes back. This equilibrium keeps the star stable for most of its life. This delicate dance between gravity and energy production can continue for millions, billions, or even trillions of years depending on the star's mass. Larger stars burn through their fuel much faster than smaller ones, leading to different lifespans and end-of-life scenarios. However, the star's fuel reserves are not infinite. Over time, the hydrogen in the core is depleted, and the star must find new ways to sustain nuclear fusion. Eventually, the star will run out of hydrogen, the primary fuel for nuclear fusion. When this happens, the core contracts under the force of gravity, leading to higher temperatures and pressures. As the core contracts, the star's internal structure begins to change dramatically. Helium fusion starts, and the outer layers of the star expand. For stars like our Sun, this process leads to the formation of a red giant and eventually a white dwarf. The outer layers are shed, creating beautiful planetary nebulae, but for more massive stars, the story takes a more explosive turn. These stars can fuse heavier elements in their cores, leading to a series of increasingly unstable reactions. As the core collapses, it triggers a shock wave that propagates through the star's outer layers. This shock wave is powerful enough to blow the star apart. This shock wave is responsible for the brilliant outburst of light and energy that we observe as a supernova. The explosion disperses elements into space, contributing to the cosmic cycle of matter. In the case of hypernovae, the core collapse is even more violent. These rare events are thought to occur in the most massive stars, leading to even more dramatic explosions. The exact mechanisms are still being debated, but it's thought that the core collapses directly into a black hole, or that it forms a rapidly rotating neutron star called a magnetar. These remnants are incredibly dense and have strong magnetic fields. These extreme events release even more energy than supernovas, producing gamma-ray bursts that can be detected across the universe. These bursts are among the most energetic events known, providing valuable insights into the life cycles of stars and the dynamics of the cosmos. Our understanding of star explosions has been revolutionized by advancements in telescope technology. These technological leaps have allowed us to peer deeper into the cosmos and capture phenomena that were once beyond our reach. We've gone from observing these events with the naked eye to using sophisticated instruments that can capture their light in unprecedented detail. This transition has opened up new avenues for research and discovery, enabling us to understand the life cycles of stars in ways that were previously unimaginable. Ground-based telescopes, equipped with adaptive optics to compensate for atmospheric distortion, provide ever-sharper images of supernova remnants. These adaptive optic systems correct the blurring effects of Earth's atmosphere, allowing astronomers to observe celestial objects with remarkable clarity. But perhaps the most significant advancements have come from space telescopes. Freed from the distortions of Earth's atmosphere, these instruments can capture the universe in stunning detail, revealing the secrets of distant stars and galaxies. The Hubble Space Telescope, for example, has been instrumental in observing supernovas in distant galaxies. Since its launch in 1990, Hubble has provided a wealth of data, helping scientists to map the expansion of the universe and study the aftermath of stellar explosions. Its high-resolution images have allowed astronomers to study the expanding debris clouds and learn about the composition of the exploded star. By analyzing the light from these remnants, researchers can determine the elements produced in the explosion and gain insights into the processes that drive these cataclysmic events. The launch of the James Webb Space Telescope in 2021 marked a new era in astronomy. With its advanced technology, JWST is poised to answer some of the most profound questions about the universe. With its infrared capabilities, JWST can peer through the dust and gas that often obscure supernovas from visible light telescopes. This ability to see through cosmic veils allows astronomers to study the birth and death of stars in unprecedented detail. This allows us to study the early stages of these explosions and gain a more complete understanding of the processes involved. By observing these initial moments, scientists can develop more accurate models of stellar evolution and explosion mechanisms. Moreover, neutrino detectors buried deep underground and gravitational wave observatories provide new ways to study star explosions. These cutting-edge facilities are opening up new windows into the universe, allowing us to detect and analyze phenomena that were previously invisible. Neutrinos are elusive particles that are produced in abundance during supernovas. These ghostly particles can pass through matter almost undisturbed, making them incredibly difficult to detect. By detecting these particles, scientists can gain insights into the conditions at the heart of these explosions. Neutrino observations provide a unique glimpse into the core collapse process, offering clues about the physical conditions and dynamics at play. Gravitational waves, ripples in space-time caused by the acceleration of massive objects, offer another avenue to study the dynamics of core collapse and the formation of black holes and neutron stars. These waves carry information about the most violent events in the universe, allowing us to probe the fundamental nature of gravity and the behavior of matter under extreme conditions.